Hi, let us discuss Article 120 this time, okay? Two tritangent centers divided by sector on which they are located harmonically. Um, to be able to prove this effectively, or to understand it effectively, it would be best that we go back to elementary geometry and recall the angle bisector theorem, and we'll prove them, okay? This is the internal angle bisector theorem. This is what we are familiar with. The internal bisector of an angle of a triangle divides the opposite side internally in the ratio of the sides containing the angle. So this is angle A, and we have the angle bisector AD. Thus, angle 1 is congruent to angle 2. So what it says is the fact that this segment BC is divided into two segments, BD and DC, and the ratio of BD to DC is the same as the ratio of BA is to AC. Thus, BA is to AC as BD is to DC. If you recall, to prove this, the best way to do is to construct a triangle, which will turn out to be an isosceles triangle. But that is only a consequence of constructing a line parallel to AD passing through C. So that's the one that we've got in here. So construct a line parallel to AD and passing through C, okay? And hence, if that happens, then it seems like this angle is congruent to this angle, and this angle is congruent to this. But 1 is congruent to 2, and therefore 3 is congruent to 4. So one more time, we have the first one, construct CE parallel to DA, and then angle 1 is congruent to, that should be angle 1 is congruent to angle 4, because they are corresponding angles. Next, angle 2 is congruent to angle 3 because they are alternate interior angles. But angle 1 is actually congruent to angle 2 because AD is an angle bisector. Thus, angle 3 must be congruent to angle 4. But wait a minute. If you look at this big triangle and this smaller triangle, they are similar. And by triangle proportionality theorem, we have BD is to DC as BA is to AE. But instead of using AE, I will replace it with its equivalent value, which is equal to AC. Hence, we are able to prove this one, okay? Now, but that's only one aspect of this theorem. We also need to consider the not so popular external angle bisector theorem, but this is nothing but a repeat of the angle bisector theorem, but this time we will just extend it to external bisectors. So here's my triangle, and let's consider okay, let me consider first. So I extended ray BA, and therefore I bisected the external by ray AD is the external bisector of the triangle, one of the, so that's what it is, okay? So that's what it is, and therefore, okay, so just like what we did here, we constructed CE parallel to DA. Let's do that too. So this is my yellow triangle. I would like to construct a line parallel to this pink one. So that's what it is. So I constructed a line parallel to AD passing through point C. Now, with that, what will happen is that, okay, angle 2 is congruent again to angle 4 because they are corresponding angles. Angle 1 is congruent to angle 3 because they are alternate interior angles, and therefore 3 is congruent to 4, and hence triangle AEC is once more an isosceles triangle. Okay? So this is an isosceles triangle. And by triangle proportionality theorem, which one is similar triangles? BEC is similar to triangle BAD, and hence I can now use BD is to CD as BA is to EA, and instead of using EA, I will use AC. Okay, and hence we have this triangle angle bisector theorem and the triangle angle bisector theorem. One is for internal and one is for external, but they are totally identical to each other. And thus, all I need to do is to apply that to this particular theorem. So, here is my triangle ABC, and let's consider two tritangent centers. And I started with I sub A. Okay, so let us define first points U, V, and W as shown. So these are, because I want to consider segment BC with respect to A. So this is the point that I'm talking about. So that's point U. So if I consider tritangent centers I and I sub A, that's what we have. So it will be I will be dealing with the lines that are collinear with I sub A, and that is A and U. So thus, BA is to BU. Keep in mind that this is an angle bisector, is equal to AI is to AU. But this is an angle bisector, and therefore it's the same thing as A I sub A times times U I sub A. Okay? Let's hide that. Okay. And that's what it is. But at the same time, I can make use of this particular triangle also, because this is an angle bisector also. So I can say CA is to CU. And you notice these are the computations I've done, and no matter what, the values of the ratios are all the same. Okay, the values are all the same. Now I can do the same process, but this is just nothing but a confirmation. Okay, so BA. So this time I'm using IIB. IIB. So that's this one. If that's the one I'm using, then it's collinear with B and V. And in that case, I will use either this triangle or that triangle. Okay. If I use this triangle, then I have BA is to AB as BI is to IB, or BI sub B is equal to VI sub B. Using this triangle, that is the same thing as CB is to CB. And the constant ratio this time is 1 is to 1.55. Okay? And using the same line of reasoning, I can do the same thing for IIC. IIC, that means I will be using this triangle AWC or BWC. Okay? But the ones that we've got is, instead of using center I will be using the other two. Example, I sub B, I sub C, then it has to be collinear with point A and another point here. So that needs some more triangle to be defined. And that is, now let me extend the triangles. So here it is. So I need to define So now I need to define U prime, B prime, C prime, that is on the extended sides of triangle ABC. Okay, on triangle ABC, we have here point U. On the extended side is point U prime. And then on triangle ABC, on side AC, we have point B inside. On the exterior point, or the extended side, is B prime. And finally, somewhere here. So I need to change this. There you go. And on side AB, I have a point W, and on the extended side is W prime. Okay, so let's try to show it one more time. There you go. I want to see UW. So here it is. So I'm going to use now I sub B and I sub C, and it's collinear with this one. And in that case, I need to make use of point B. Okay, so that will be BU prime times BA is equal to U prime I sub C, and is to A I sub C as U prime I sub B is to A I sub B. That is making use of B. This time I can make use of C. Okay? But everything is the same, and that's how beautiful this theorem is. Thank you very much. See you next time.